took this last chance of squeezing some of his wisdom out. Please.
Thanks very much, Epifanio, and yeah, I'll be leaving in a couple of days, so let me start by expressing all my gratitude to John Ball and the other organizers, first of all, for putting together such a wonderful institute, and also for inviting me here. I certainly enjoyed it very much. I'd like to stay more. The talk today is on, in a way, a continuation of something that we've been discussing during the workshop, and it will be on molecular organizations of liquid crystals, and if I have time, I'll put in also some molecular crystals on kind of a bulk scale, meaning not as bulk as a kind of centimeter cube, but it could be anything down to micron cube or more, and of course nano, which is interesting now. We will deal, as we heard during the institute, with two types of models, basically, molecular level models and atomistic models. And the first is basically a generic type of model, more a physicist or a mathematician, if you like, type of model, where you replace a kind of realistic model with all its atoms, partial charges, dipole, quadrupole, polarizability, with a simple object. And maybe you endow this simple object with a shape which is reminiscent of the shape of the real molecule. So if you want to do liquid crystal, it would be kind of wise to have them elongated or anisometric anyway, for example, deschotic or elongated. And you could have a spherocylinder, you could have something else. We rather like this ellipsoidal shape, and in all the talk, I will be using models where we have both repulsion and attraction. Let me comment. Of course, we do have hard particle models, and they do serve a purpose. The purpose could be, for example, to try to answer the simple question, what is the minimal model I can have to have, for example, spontaneous order? And it has been shown, well, since on Sager time and Dan Frankel with simulation, that, for example, a simple spherocylinder endowed with hard repulsion, meaning that if the molecule tries to overlap, the potential will go to infinity, but it will be zero. So if there were spheres, it would be like billiard balls, right? That model is enough to give you an nematic, for example, from cooling, or well, not cooling, from increasing the density, because the models are athermal, being either zero or infinity. If you put them in a Boltzmann factor, they will be, yes, you will be making the temperature irrelevant, which is part of the problem if you want to study thermotropic liquid crystals. Moreover, purely hard particle models cannot explain things like surface tension, or, for example, the fact that if you pull a liquid, you can exert a certain quite important negative pressure before breaking the liquid. For water, you can go to 500 Pascal or something like that. So we like attractive and repulsive. And being anisotropic, if you want to generalize kind of simple Lennard-Jones 612 interaction, then the more successful model, there have been many attempts, it's not trivial, even Bern did more than one, is this model which was due in original form to Gay and Bern, where the shape is still 612, but of course you have a contact distance which is dependent, like the potential in general, on the orientation of molecule 1, of molecule 2, and on the intermolecular vector. So if you approach two molecules side by side, right, the interaction well depth may be very much more profound than if you come end to end. And these are really so well known and done in the literature. The purpose of these couple of slides here is just to show that the form of the contact distance is really analytic and very simple. So it's easy to program. And if you cut, I mean, you have a couple of parameters that dictate the depth of the potential well, and you may tune that, for example, by inputting some quantum mechanical calculation, but that is beyond the purpose here. I'll show you the two parameterization which are most popular. The original one, where these two molecular parameters, if you like, these 2, 1, don't mean very much in themselves, but they make this curve, the dashed one, which means that side-side is, yes, deeper, but not that much. We favor this other one, which has a much stronger side-side interaction, which is more similar to the one of real molecules. And they do actually give a wider nematic phase. So by these simple models, you can do simulation. You can build the bulk organization, isotropic, nematic. The smectic are formed spontaneously, just cooling down. And when we mean bulk, we still do samples of, well, maybe a few thousand particles. Now with this type of modeling, we can do easily a few millions. But, I mean, it's not as easy as doing Lennard-Jones. It's still more than an order of magnitude more complex, because you go from a distance to 5 variables, right? It's a lot more complicated. And so to mimic bulk, if we are interested in bulk, the trick that is nearly universally used is to replace the vacuum around your sample, but cut by copies of your system, of your sample cell, which means that you are inserting in your system some spurious periodical fluctuation. One should always remember that if you have a box of size L, it is kind of meaningless to go more than half box, because you're just picking up the correlation with the image of itself. And also in time, it is kind of meaningless, apart from the difficulties in performing the simulation, to do time windows that are longer than the time it takes to the speed of sound to go through the box and come back from the other side, right? In practice, for a long time, these have been kind of meaningless because you couldn't do them anyway. But now, one has to be kind of careful. So if we want to do bulk, then we may calculate, for example, the orientation order parameter, the Q-tensor, whatever, or actually the full orientational distribution, for example, the single particle one, and expand it in the first few moments would be the order parameters. So you would be, for example, picking up that you have an isotropic, nematic. Of course, the smectic would require one more order parameter, and we'll talk that at the last part of the talk. But, you know, you have a little blip here, which suggests that you have something. And you do have layering, of course, which corresponds to the smectic. So now, in the talk, I'll try to pick up examples that have to do with interfaces. And I'll try to show you a few interfaces, a few important interfaces. The nematic isotropic one, of course, is an important one. So you could say, why? This is fine. We have a simple model. We just do a calculation and predict what the interface will be. Meaning, for example, what will be the orientation of the molecules at the interface, if I have an interface? Will it be perpendicular? Will it be planar? Will it be tilted? And so, for simple models like hard rods or this ellipsoid, there have been a number of theoretical attempts giving different and even contradictory results, starting from the same potential, which is kind of embarrassing. So we thought it would be nice to do a simulation, because the simulation would give us an answer, at least a numerical answer. The trouble is, it's not easy to actually make this nice flat interface, isn't it? Because in simulation, if you did cool down, and your system is so small that rather than phase separating, often you get fluctuation in time between order and disorder, and it's really... So we use the trick, and the trick is similar to what experimentalists often do when they want to study a lot of simulation. They take kind of the sample in the form, say, of a glass slide, and you clamp the glass slide at two ends, and you make the temperature at one end slightly higher than the transition, and the other end slightly lower than the transition, so you have a gradient, and somewhere in between there will be your phase coexistence line. And what they do then, they just act on a microscope or a polarizing microscope or whatever. So we thought it would be nice to do that. And of course, we do have a problem in that having kind of 10,000 molecules or so at the time we did it is a long time ago. So I'm just putting in to give you a complete picture. The number of molecules of the order of 10,000, 12,000 that we used was not enough to allow us to have many buckets at different temperatures. So we took two. So half of the sample is a T nematic isotropic that we have determined before, minus, and the other plus dt. And in molecular dynamics, which is just a solution of the equation of motion, you don't have temperature, right? Because Newton didn't know about the kinetic interpretation of temperature. So temperature is inserted by scaling velocities, right? And remembering equipartition principle, so that every degrees of freedom gets a kT over half. So if you want to change the temperature, you can scale the velocities, maybe pick them up from the Maxwell distribution. So every time a molecule goes through here, we scale its velocity so that we thermostat these at this temperature slightly higher and this slightly lower. So can we do that? These are just technical detail. I'm putting them here just to as a reminder, but I think you can see the answer immediately. What is the orientation at the interface for this model? It's kind of planar, isn't it? Because it's isotropic here. I forgot to tell you that the color here, the molecules are all the same. The color indicates the orientation of the molecules picked up from a certain palette, which in this case is the one represented here. So the simple answer is that you can make it more quantitative. For example, we can plot the order parameter obtained from the eigenvalue of the ordering matrix. So the order parameter with respect to the director, if you like, the local director, and you see that it goes through here. And we can also have the order parameter with respect to the interface normal. So this can become negative, expressing the molecules being perpendicular. So here is isotropic, basically. You notice the effect of the periodic boundary condition. This is irrelevant. It's just the coming up of the other parts, right? But if you look from here, so to half of the box, it is isotropic here, and it becomes negative, which means that the molecules are perpendicular to the layer, to the interface, normal in this case. And the transition is a weak first order, as we know. We can plot the density and fit it to the usual hyperbolic tan function, and we can measure the width. The width of the transition is pretty large. In this case, is comparable to half of the box size. It turns out that it is much larger than the one that you get, for example, for Monsager hard particle type models, where the transition is stiffer and consequently the width of the interface region is lower. Here it is about, if I remember correctly, 4 times the molecular length, which is pretty, if the molecular length is kind of 2 nanometers, it's pretty large. So other interfaces. Well, pneumatic vapor. You could say that again, this is trivial. I'll point out the little difficulties that there are in the business. Well, it's not so easy because, first of all, you have to have a pneumatic vapor interface. This is not necessarily a law of nature that you have. You could have different phase diagrams. The topology could be different. So, for example, you could have a situation where to go from the pneumatic to the vapor, you have to go through the isotropic liquid anyway. Or you could have this one, which is the one we would like, where you have a region of the phase diagram where you can actually go directly pneumatic vapor. So the standard Gay-Byrne parameterization that does not give you that. And it was very useful, this study of De Miguel and De Rio, which showed with a different parameterization you can. We actually studied this a long time ago and observed, we want to know, again, what is the orientation of the pneumatic vapor interface? And we shall use it later on. More recently, we've used it later on. Now, once more, in simulation, you have to make sure that what you see is kind of equilibrium. So you have always to work against the easiest path to solution. So if you want to see a pneumatic film formed, it doesn't make a huge amount of sense to actually have a pneumatic film to start with, because you could say, well, it's just there from the beginning. So to confirm that we do have the separation, we filled up the cell, and I think it's a convincing way of doing it in general, even though it takes time. We filled the cell and let it evolve. And you see that if you've got the right thermodynamic condition, of course, you get at a situation like this, where you are just above, just below. And it seems clear that what you have here is a planar interface, tangential boundary condition. So this was a long time ago. We used this recently. I showed this in another talk, but I would like to show it now as a consequence of the kind of interface that we have. So here we study the formation of pneumatic droplets from the vapor. And we do have a condition where we can have vapor in equilibrium, and we know that we have tangential boundary condition. So we did this. You start from a cubic droplet, just to be sure that it will not end up the way you started with, and let it evolve. And from now on, I will not show the vapor molecule, just to avoid the cluttering of them. So one thing that we wanted to investigate was the shape of the droplets that form, because for liquid crystal, you know, it's not obvious that you should have spherical droplets. You could have tectoids. You can have different shape. And moreover, we wanted to see if we could, at this nanoscale level, these are droplets of the order of tens of nanometers, if we could have spontaneous breaking of chirality symmetry. The molecules are not chiral. If we could have the formation of chiral droplets. They had been observed in large droplets, for example, by Oleg Lavrentovich. And there is a whole theory by Prince and Van der Schott, where they have, on the basis of different elastic constant, the possibility of having droplets of different kinds. Let me show you what we get. This is not continuum theory. So first of all, we can check if the droplet is a bit of uniform material, which it is not, because it has a different order parameter inside in the interface. It's reasonable. You can follow equilibration in this reduced time. You see that after a while, the number of molecules in the gas, also the vapor rather, the core and the interface is coming to kind of stationary state, stabilized. And we can see the effect of changing size. And we can actually see that in certain conditions you do have chiral droplets. Let me see how we can make sure that they are chiral. We can measure a simple pseudo-scalar that would go to 0 and be of opposite sign for left-handed and right-handed. And we can see that spontaneously, by chance, if a droplet starts to be left, it will continue, and if it starts to be right, it can continue. So by making histograms of this chirality index here, we can actually, where n is the director, r perpendicular is the position of the molecule we consider molecule I with respect to the axis, and z, of course, is the axis. So we can have histograms, and we can check that actually, even though you can be chiral, of course, you can equally be left or right. The chirality is strongly size dependent. So we have no chirality for small drop. If we go to kind of 100,000 molecules, then you can, 100,000 molecules may seem a big number. It's not that big. I mean, it's kind of below, still below the attoliter. So it's lower than kind of, just to give you an idea, your inkjet printer will print kind of typically picoliter, which is a lot more. But still, this is kind of 100 nanometer by 100 nanometer by 100 nanometer cube. So and then the aspect ratio of the droplet changes. It becomes more spherical. So we don't know. I mean, we have not pushed it until. But it is kind of nice to see the emergence of things like chirality from nothing. And of course, if we had the polymerization or something stopping the evolution of the system, they would be there forever. Half-life left, half-right. Now, so we've seen nematic isotropic, and we've seen nematic vapor. And of course here, sorry, I didn't comment on the fact of the chirality. What does it make physical sense? Well, it is, I think, meaningful because when you have this shape, tectoidal shape, the molecules here, for a tangential condition, have to splay near the pole. They have to open up. If the elastic constant for splay is not favorable, to go from here to here, rather than go directly, have a bipolar system, they would do what you do when you go up in a mountain. You would twist and go up. So solid state nematic. I'm still talking about this gay Bern, so molecular level model, where the resolution is that of one particle, one molecule replaced by an object. So here we have taken the droplet that we've just formed, and we deposited. This is just still to be published. This is recent work, and we have deposited on a surface. So let me show you first, maybe a little video of what, and then comment. So you see the droplet is coming on a surface made of 001 on an FCC lattice of Lennard-Jones, and the droplet is anisometric. It has actually two different contact angles in the two directions. But notice also this effect, that the droplet kind of deforms, doesn't really rotate, but deforms and move so that it goes along the along the diagonal direction, because it picks up more centers in that way. It can interact with more molecules, right? Now, if we now look at the contact angles, go back to the, so we can start, of course, having our droplet put down in one way or the other, but you end up with the same. This is the video. We can get contact angles. It's not that simple to get them from simulation, but you can build, we use a, well, we fit to a certain curve. We use a method that was, and we fit in the two perpendicular direction and get contact angles parallel and perpendicular to the axis of the droplet, if you like. We can also change the interaction with the surface, which is this parameter here. So we can go from a kind of, let me say, hydrophobic, even though there is no water in here, a kind of situation with the contact angles greater than 90 to a complete wetting type situation, changing the strength of the interaction. Now, the contact angle, the two contact angles do change with temperature, and they become equal as you go over the nematic isotropic transition, and then as we cool down, they become different again. So we can plot the average contact angle with respect to the surface of the nanodroplet, and as a function of the strength of interaction with the surface. So the idea is that you could model the effect of changing your surface and making it more droplet-philic, as it were, right, and vice versa. So, droplet with solid. Now, suppose the droplet, of course, has free vapor on top. Now, suppose that you have a nematic inside a cell, and the cell is a thin cell, relatively thin cell. So now we consider the case of the effect of solid surfaces on the order of the nematic in a kind of nano-confined environment. Okay? And again, we do it simply. So we want to treat different walls, and to do it in a kind of uniform way, we take, again, our simple Gabor model, and now we put two centers here, A and B, two simple interaction centers, and they will describe the interaction of this particle with the wall. So we can have a variety of walls. I mean, this doesn't look so good. There are two terms because there are two centers. Notice that it is not the 612 because it is an interaction with the wall, so it is a different exponent type. But it's an attractive and repulsive interaction between the sites on the particle and the wall. And here we have an angular term and the strength term. And so by this simple form, we can have a repulsive wall, a random planar wall, which is actually practically the same except for the extent of the interaction, a uniformly aligned wall where you have a preferred direction in the surface, and we can have, by changing the angular factor, an homeotropic aligning wall of weak and strength, a weak and strong kind of interaction. So very quickly, the dimension is of the order of 24 times the molecular thickness. So if this is 5 angstrom, you can see that we are in nano range. And you know that in nano range, properties do change. So if we look at the transition temperature, which is this dashed line here for the bulk, 3.57 more or less, we see that we have two types of surfaces. Well, it's reasonable, isn't it? The uniformly aligned and the homeotropic are like applying a field. They break the symmetry, so they have a kind of supercritical behavior. You have order also in the would-be isotropic phase, right, like in many other cases. And the other surface is kind of making it more difficult to order. So it has a depleting effect on the order parameter. So uniformly aligned surface, we shall see something similar with fully atomistic, increases the order. This is not the order of the surface right now, it's the order of the whole cell, right? And the other decreases. But the effect is noticeable. So, say, to summarize, kind of repulsive wall, we still have a weak first order transition, a random planar, homeotropic, uniform. The transition looks like more second order, and the pseudo transition is kind of slightly modified and lower here. We can look at pictures of the snapshot, and we could look at the pair distribution from the wall, the radial distribution from the wall, and we see that, of course, the homeotropic has a peak. Well, the molecules like this, so we'll have a peak further away, about 3, which is the length of the molecules, and it will induce some kind of smectization at the in a nematic region. And this is a uniformly aligned, the red one, PA. In the isotropic, there is some induction of order from the wall that permeates. So, again, these are data that might be used for building approximate theory. I mean, the kind of general idea is that you have data, in this case, for simple models, and these simple models could perhaps test theories. So if the simulation gives you a planar alignment and your theory predicts perpendicular, then, well, maybe we should both look at, at the data, but the simulation normally are pretty robust. The other in the last part of the talk, the other thing I would like to show you are atomistic models. And they pose a kind of much bigger challenge computationally, really kind of quite large. But on the other hand, they play the role of virtual experiments. So we can compare with kind of real molecules, real experimental data, and maybe learn something. So I showed in another talk that how easy it is to modify the structure and obtain huge differences. So I'm not going to show that again, but I would like to concentrate on the fruit fly of liquid crystal, on the cyanobiphenyls, this type of molecules here. And, well, basically because I did a little search, which has disappeared. But I did a little search in Web of Science this morning, and if I put 5CB, oh, clearly I dropped it. But I was surprised to see that if I put 5CB, 6CB, 8CB, which, as you know, is the short name for this, I got about 2,000 papers, which is a kind of, for our field, a pretty large, substantial number. No, it's gone somewhere. Of course, it will come out immediately after, but that is there, it's hiding. It's Murphy's Law, isn't it? That's was that lost in citation? That's even better. I like lost in citation. So anyway, 2,000 papers. So it is kind of reasonable to use this. And the general approach in atomistic model is different. You don't invoke a simple object to replace your molecule, but you try to take the molecule in its complexity. So you have maybe one little van der Waals type sphere for every atom, and you work out first by quantum mechanics your partial charges on every atom. You work out your basic geometry. If the molecule, like nearly always have, any particular cyanobiphenyl have a torsional degree of freedom, or they have a chain, you work out this torsional potential. You fit them to a Fourier series so that you can easily calculate, reconstruct the potential at any point in time where you need it. And once you've done that, which is called building a force field, then you solve Newton's equation of motions, basically, using either one of the available engines or one that you write yourself. And you use, well, as large as your computer as you can hold, because kind of we're talking in the region of kind of 1 million hours of one processor for kind of one chemical formula, if you like, kind of order of magnitude. as you know, there are about 8,000 hours in a working year, so it's kind of, if you were using one processor, it would be pretty busy for kind of 100 years, something like that. So you have to use, of course, parallel computing to a large extent, massive, as you say. So HPC. So can we do, first of all, the simplest challenge? Here is the formula. What will be the transition temperature? In other words, your friendly organic chemist comes to you and says, this is the formula. Will it be a liquid crystal? At what temperature? And you know, this is difficult for water even. If I give H2O, 25 years ago, Maddox, the editor of Nature, said it was a scandal, a scientific scandal in a famous paper, that you could not predict it from H2O. We think we know everything about water, isn't it? But of course, from one molecule, you cannot give a transition temperature, so you have to have a collective n-particle system, and that is quite troublesome. So anyway, the first challenge was, can we do it? I knew it was there. Found the citations. Yeah, it was 2000 and something, and counting. So this series is challenging also because if you take this chain to be 4 terms, C4, it doesn't give you a honest-to-God reversible liquid crystal, but 5 is the 5CB that we all use, and 6 and 7 and 8 are nematic, and the 8th gives the smectic for the first time. So the other challenge will be, can we get a smectic? And this has been investigated by a number of people also theoretically, by simulations, and I just put a list to show that there have been a lot. So if you now do your simulation, choose a temperature. Now this is not reduced temperature, this is real temperature. Maybe right or wrong, but it is real degree Kelvin. And then you repeat the simulation at a lower temperature, and then you repeat at a lower temperature. You see that the system becomes ordered. And it's a 5CB, so it shouldn't give a smectic. If you look at some recent papers, you find models of 5CB that gives a smectic. If possible, I would tend to avoid models that have, on one end, claim realism, and on the other, give you a different phase sequence, right? So the model should give nematic, not necessarily smectic. And it does. So if you take trajectories which are long enough, you can start from isotropic and, you know, spontaneously ordered, or if the temperature is higher than the transition temperature, spontaneously stay disordered. We can compare. This is bulk. So this is just to show that we can compare now with real data for density, for order parameter, for NMR dipolar coupling, both for the core and for the chain, dielectric constant. And this is, for example, a comparison with birefringence, showing that 3 sets of data from 3 different groups have between themselves similar differences to what we have between our data and their average. So it's kind of not much worse than experiment. And it has some predictive power. So for example, P4, the 4th moment in our simulation, was positive. In an old paper was by Picken and others was negative here. But more recent data, after we published the paper by the group of Gisselman and Misha Osipov also contributed to the analysis in Stuttgart, this is Raman depolarized data. And you can do it with a different laser power. And the lower the laser power, the better, because so in these 2 series of data that they have, the one that is more similar to ours is the one with the weakest power. So again, I think this is now pretty convincing evidence, I think, that P4 is positive for all the temperature region. And the transition temperature that deviates from experiment for not less than 5 degrees, which is kind of satisfactory. So how do we locate the transition temperature? Because when you have a finite system and periodic boundary condition, you always have a continuous transition. So it always looks second order. Well, if we remember that at the classical picture of a first order transition in Landau-Desgen's theory, we have, for the first order, 2 peaks of the free energy, one isotropic and one the order parameter of the transition at exactly the same depth. Then if you have many, many, many instances of your sample, your instantaneous values of your order parameter, you should have a 2-peak situation. So if you are far away from the transition, only one peak at the order parameter. But if you are close to the transition, you have two peaks. So we try to locate the more close two-peak situation that we have for each case. And that's the way we locate the transition. Now, this doesn't come easy. And again, a word of warning, because it's very easy to pick up, to go to the website, you buy a commercial product, or you download one open source. It says molecular dynamic atomistic simulation. You type your geometry, push the button, you have enough computer time, wait, get results. It doesn't work like that. Because the force fields available are typically tuned for proteins, for bio. Some are tuned for material, but different material. If you take the standard, say amber or something similar, they are wrong. You get the transition temperature wrong by kind of more than 100 degrees. And sometimes it doesn't matter. So there are recent papers where the transition, for good reason, I mean, I'm not criticizing, I'm just giving, I mean, for example, in this case, they switched off electrostatic forces, so obviously you don't get it. It's about 70, 80 degrees off. In this case, they were not interested in determining the phase transition, but still, it's kind of 75 degrees. In this case, again, there wasn't, so, I mean, there is a, this is kind of nice, because David Earle did, kind of a year and a half ago, a series of compounds, and they showed very honestly the simulated result and the experimental. So simulated and experimental, simulated and experimental. And I think if you look at the scale, you can see that they are wildly different. So word of warning is don't just do that. The force field has to be tuned. Careful quantum mechanical calculation has to be done first. Comparison with real experiment has to be done. And then things like the size, the partial charges have to be tuned. But then once we have done that, we have kind of an experimental system, so we can do experiment. Now, can we get a SMACTIC? This is just coming out in JChem Phys. Yes, we can get a SMACTIC for HCB. We can get the density. I'll quickly go over this. We can get the order parameters. Again, they are in good agreement with the experiment. Okay, so if we can locate the transition. You see the histogram of the order parameter. Here is one peak, and that the transition starts to show, the system wants to be both isotropic and nematic. So you see this building up a tail here, but then it's definitely nematic. Nematic, the SMACTIC you don't really see very well, but if you do a kind of careful analysis, you get the SMACTIC transition also within a couple of degrees from experiment. We validate with the layer spacing. HCB is strange. I mean, if you look at the formula, CN has a strong dipole, about 5 dBs. It should pair like this, but it doesn't. It pairs like this, because the dipole is more diffuse. And actually, it is kind of this. And so the simulated layer spacing is 32 angstrom, and it compares with 3 independent sets or 3 different groups, which were 31.6, 31. So, I mean, it could be better, but I think it's kind of very reasonable. And it is temperature independent, essentially, like experiment shows. Now, there is an issue here of positional order parameter, which should be trivial. It's not. We obtain it in 2 ways. One, let me say what the issue is in simulation. Because things, when you go from theory, we also do theory, but when you go from theory to simulation, there are things that you take for granted that are not obvious. For example, if you have a simulation, every time you have a snapshot of your system, right? Okay, your layer spacing on the average is 32 angstrom, but who says that that particular snapshot does not have a fluctuation that brings it bigger or smaller? And okay, you have layers, but who says that the phase factor is the same in every snapshot? It could be shifted. So you have to find ways that are translational invariant in the same way as we calculate scalar order parameter for the eigenvalue in a similar way, of course, not in the same way, from the eigenvalue of the Q matrix, right? Because in that way, we make ourselves independent on the instantaneous fluctuation of the sample. So anyway, if we do that, we find that the order parameter is lower than the claimed experimental one, which is basically from X-ray and neutron scattering data. In the paper, we have an analysis of why that might be. And in a nutshell, I think the analysis of X-ray diffraction data basically assumes that you have translational order parameter but doesn't bother with mixed orientational translation order parameter. If we calculate that for a system like HCB, this kind of mixed parameter is kind of similar to the pure translational one. So if it goes into your analysis of the result and you don't actually allow for it, you get an higher order parameter. Okay. Anyway, this has to be done probably in collaboration with experimentalists. So anyway, now interfaces. So we now have 5CB, and we would like to answer the kind of basic question. I mean, in devices, in displays, in most practical uses of liquid crystal, we are never far away from a surface. And the surface, of course, provides anchoring, provides alignment, so the molecule will align at the surface. And how? Well, normally there is an empirical parameter, or maybe a boundary condition, maybe a strong boundary condition, I think Dirichlet condition, or whatever. But in practice, is it possible to predict what it will be? So here we have taken a silicon surface, hydrogen terminated, and we have a slab of about 6 by 6 nanometer, and with a certain thickness. So this is the 001 phase of this silicon. And then we build the potential by having our molecule at different orientation, positioned with respect to the surface, doing a quantum mechanical calculation and working out the potential, right? Then once you have collected this, you see the interaction is pretty strong. This is 60 kilojoules. It's, you know, what is it? Nearly 3 eV if you think it's, I mean, it's big. It's kind of a chemical bond. So it goes planar here. The vacuum instead gives a strong anchoring perpendicular to the surface, and that's the order parameter. And did I start 5 minutes after? Yes. So let me summarize the conclusion of the findings. Here we have two different films of nematic on the silicon. One is 10 nanometer, more or less. The other is 20 nanometer. So they are in a range which can now be studied experimentally with different techniques. This is the scalar order parameter as a function of distance from the surface. And we have two nematic, sorry, say that for the thinner film, we have one nematic, one isotropic temperature, and the same for the thicker film. So that's why the two curves here terminate here. Because, of course, the film terminates here, and here it terminates here. So what we see is, first of all, that if we take the order in the middle, this is very similar to the bulk order. So this extra order is induced by the surface. So the crystal surface is actually ordering our liquid crystal, and the order here is pretty indifferent to thickness and to temperature even. It's really pretty much surface induced. If we look at the other surface, also we have an effect. The vacuum is actually a pretty strong anchoring. I mean, I think I showed this in the previous talk, but maybe just for consistency, I could quickly mention that there are different, I think, continuum-based models in the literature by Peter Polfi, by Barbero and Barberi, and probably someone in the audience, maybe Tim, you had one as well, I'm not sure. But certainly you can imagine different limiting situations where one of the two surfaces, here they are hybrid, right, planar and homeotropic, is so strong that it wins all over. This is not the case. Then you can have a continuous bend like this, or you could have a discontinuous transition with a wall. And what we find for the thinner film is very similar to the discontinuous. The change from homeotropic, from the air, to here takes place in about 5 angstrom, sort of a molecular length. This is even just for 20, 22 nanometer. This is already pretty continuous. But as I mentioned previously, rather than being just bend, what we find is that if we look at the director component, it's more clear. We find that we have twist and bend to go up. If you look at the director components, they start, this is for the thicker film, they do start equal, they go along the diagonal, the 1-1 direction, but if it did go up like this, they would stay similar. They don't. One grows, the other is small. It's a rotation, which is again kind of reasonable. And this is consistent with the experiment of Musevich on another system with the same geometry, where they find that with an atomic force microscope, if they push the system down, when the gap between the tip, which is homeotropically inducing because it's treated with a surfactant, and and the surface, when the gap is of the order of 10 nanometer, you have a sudden drop because the orientation changes from this to the flat one. And then you start to, again, have repulsion again because you just cannot push beyond the molecules. So anchoring. There isn't a prescribed way of getting the anchoring. The way we propose is simple. It's this. We build a probability density distribution of finding the molecules at a certain distance from the surface and at a certain orientation. So this is just a close-up of this region here. You see that the region with cos beta equals 0, so planar is the only one really populated in this case. And then as you go to the toward the vacuum, you start to have that the two plus or minus cosine, plus or minus 1 cosine, I mean homeotropic orientation, become populated. But we do have this thing here. So if we consider, in the spirit of the mean field theory that we heard, this is a post facto mean field theory, if you like, that this is created by a Boltzmann potential, e to the minus, say, W, an anchoring energy over kT. By taking the log of this, doing a Boltzmann inversion, we can work out this work function, which is then something that we have as a function of distance from the surface, and that we could fit. This is just showing the kind of situation at the air. The molecules tend to be perpendicular to expose the minimum amount to the air, and the chain goes out. I think this is also helped by entropy, because by going out in the air, the conformational mobility of the chain would give you a favorable entropy factor, everything else being the same. So if we then take this effective potential and we then expand it in a Legendre series, and we say we want it to truncate, we get the famous Rapini popular, and we get values that are much higher at the surface than the one that are typically measured, as Misha Osipov showed in his talk. This is the prediction also of simple models dating back to Dejean and others. It's of the order of, as you can see, 10 millijoules square meter. But it drops very quickly. So if you have an experiment which does not explore the very first few layers, just 5 nanometers away, you have dropped down a couple of orders of magnitude. So really, we need experiments that really probe the surface very close. Recently, there was one by Marina Rutz and Zappone where they used the surface force apparatus similar to the Zalachvili one, and they get values that are now much closer to ours. Their words are, these values that they measure are much higher than those measured for mica and for CTAB and other surfactants, blah, blah. And then they quote us saying that it's nice to see that there are values. So I think it's difficult to compare with experiments. You can find differences of order of magnitude in the literature because the techniques are different. They probe different surfaces, and very, very rarely is the surface accurately defined in experimental papers. And I think now they should. Why? Well, because I will show in a moment that the surface roughness, for example, which is normally not quoted, not measured, well, not measured in many of the literature experimental papers of some time ago, is important. this is just a slide to show that there is a dynamic effect, even though I will not talk about that. The molecules close to the surface, the very first layer, are moving slower than the other, pretty reasonable, and they are pretty free to move as long as they stay on the plane. But if they try to come out, it's a bit difficult for them. So this is a kind of plot of the persistence time in the first layer or as a function of z. You can see that the first layer has a much higher persistent time than, say, 1 kind of 10 nanometers away. So now here, this is just coming out, or probably just come out in Langmuir. We've treated, again, a similar problem. Now, what is the effect of chemical composition, and what is the effect of polymorphism, etc.? In other words, now we take silica, glass, well, or quartz. Before it was silicon. This is SiO2, right? And you can have a crystal, you can have quartz, or you can have a piece of glass. And this glass can have different roughness. Is the anchoring the same? And to what extent is it different, if it is different? So the first surface that you treat is a crystal, is cristobalite. It's one of the various forms of quartz. It's not chiral, like the normal beta form of quartz would be, but it's a cubic. And from this, so we prepare this. We prepare it so that it matches well-known lattice constant and whatever. And from this, we prepare glass. We prepare an amorphous silica glass by kind of heating up to sufficiently high temperature for 1,000 degrees, cooling down, it becomes amorphous. Then we cut the surface. We validate the radial distribution that we get with the known radial distribution of glass, blah, blah. We cut a slab, similar in size to the previous one, and we want to make it now, to a certain extent, rough. Normally, we call the surface flat if it is atomistically flat. In other words, we can define roughness as the root mean square deviation of the elevation, right? So you could, actually, what we do is we take a rolling sphere. We take a rolling sphere. This sphere, in our case, is a diameter of 1.6 angstrom, and we roll it on the sample, and it will bump up and down. We take the root mean square of that. If the root mean square is smaller than the atomic radii, we call this atomistically flat. Otherwise, we give a value of the roughness. So we make the surface rough by picking up SiO2 tetrahedra to a certain extent, and then annealing again. And this is the topography, and this is the electrostatic potential at a certain elevation on top of the surface for the two. So the two surfaces that we take have root mean square value of the roughness of the order of 1 is about 1.5 angstrom. It is ours about 3.2. It's small, but it's comparable to the roughness of the glass supporting your magnetic particle in your hard disk of your laptop. So it's kind of a technologically relevant surface if you want. And OK, so this is picture, topography, electrostatic potential. And now we put the film of, we put 5CB. And this is what quickly the results. And we get, well, this is just showing that for the crystal, it's similar to the silicon. It's planar and along the 1,1. For the smooth and the rough glass, there is some tendency of the molecule to come out. There is some penetration, of course, here, because the density now is non-zero also because of the holes in the surface here. And then this is a zoom up, and then you have a certain propagation of density. And we get order parameters, 1, 2. We get also the third order parameter different from 0. In other words, if you do a second harmonic generation experiment here, which has been done by Shen and others, second harmonic generation will be giving you a signal only if you have a breaking of the symmetry at the surface. So if the molecule point down, you get a signal. But if they are perfectly flat, you don't. So here, you get values, not small, not large, but you do get values. Now, the second harmonic generation experiment of Shen were analyzed in terms of the tilt angle, something like the boundary condition that you can put. And basically, they say, OK, the molecule of cyanobiphenols are tilted at about 22 degrees from the surface. So the point is that the data were analyzed by making this assumption, that you had a tilt with a Gaussian of about a few degrees, 5 degrees, something. But if we look at the raw data coming out, let's leave cristobalite, which is similar to that. What we have is that, for example, on the smooth glass, all this region between minus 30 and plus 30 degrees is populated. So rather than having a tilt, which would be an empty cone, right? No probability of being here. We have a kind of full cone. So the molecule can be anywhere between plus or minus 30. It would be nice to try to refit the experimental data with this kind of heaviside distribution rather than a blip. And that's, of course, even worse for the rough glass. Order parameter is increased for the crystal, decreased at the surface for the random glass. And the anchoring is again biggish, but much smaller for the rough glass and slightly increasing. The planarity of the orientation is recovered after a few nanometers. You see, this is basically planar, kind of 10 nanometers away. So, basic comments are that now we start to be able to predict anchoring direction, anchoring energy to some extent. Anchoring depends on chemical nature and morphology. Crystalline silicon and silica enhance order, and the amorphous silica reduces order. So maybe I can show you just a couple of slides, again, of warning. When you compare with real experiments, not always you have surfaces that are prepared in a thermodynamical, equilibrium way, infinite. Very often you have vapor deposition or other. So here is a case, and very quick, I just show a couple of pictures where we simulated by molecular dynamics the deposition of pentacene on fullerene, because this is of interest for inorganic electronics, these are organic semiconductors. So the situation here is very different. We have a ballistic deposition of the molecules here, but there are some interesting things. So at the early stages of deposition, you see the molecules lie flat. We're pretty happy of lying flat. When you get to about 40–50% of the coverage of the first layer, the molecules collectively stand up. And this happens to some extent also with the second layer. And this, again, matches some experiment. And it's just a warning to say that, again, I think we are going towards a situation where you have actually to use simulation, not just to predict thermodynamic quantities, but to do virtual experiment and replicate, if possible, or predict the outcome of experimental data. And let me not finish without thanking the people who do the work. So Roberto Berardi, Silvio Orlandi, Lara Querciagrossa, and Matteo, mainly for the gay burn type, and Gabriele, Luca, Antonio, and Otello, mainly for the atomistic and surface. And of course, the work would not be possible without agencies. And thanks very much to you for listening. Thank you.
I think we have time for a couple of questions.
Your chiral droplets should be biaxial, so one director is not enough to describe chiral, at least 3 directors.
Well,
it's interrelated.
It's chiral, and then it would be reasonable. But the key point here is not so much the emerging biaxiality. I think it's really the stunning effect is the fact that they are chiral. Then it's a size-dependent effect, etc. But the molecules that we put in are not biaxial. So
the order must be biaxial.
Sure. But it's so if you're looking in terms of biaxiality as averages of the D2Mn, the biaxiality would emerge only through this first two. So it would be the 220, where this is the usual real symmetrized Wigner rotation metric thing. So it would be emerge through this order parameter here.
Please, Steve.
So if we give a simple question, what fixes the size of these narrow droplets?
It's just the, well, first of all, the total number of molecules that we have in our system we fix from the outside, but the partition between the droplet and the vapor is given just by the thermodynamic that we have in that. So the size grow and then they stabilize. But we have one droplet. I use the plural, but it is one droplet at a time, right? So they have not a mean of growing by merging two droplets. They can only acquire from the... Yeah. So basically, it's related to the number of molecules that we put in our sample, because by having the wherever it was, so we change the size of our sample included, and then at that thermodynamic condition, a certain fraction wants to be condensed, right? But we can put more. Okay.
So what supersaturation is needed for the droplets to form? You probably don't know that.
I don't have a number for that. I mean, what we concentrate on is seeing first that the droplet exists, and we do this by an algorithm that counts the neighbor around every particle, right? So by this algorithm, we assign a droplet character to being vapor, if it has only neighbors to such and such average distance, to be inside, if they're close, and to be interface. And then we monitor that we have, for that sample size, for that number of particles, a reasonable stabilization, and then we...
Ibrahim?
Going back to water simulation, so
To which one?
to water simulations, a more complicated
Water
question.
simulation, yes.
So what's the story I've heard some years ago from people who simulate such systems? It's especially when they fine-tune the force fields. What often happens, you do one thing, and that predicts certain phenomena very well, but then it fails in the others. Like you can get surface tension, fail, critical
Yes,
temperature,
yes.
get that one. So does this happen, and what's the...
For water, it does happen. For example, the most popular force field, T3P, T4, T3. I mean, some of them predict very well certain properties and not others. This is kind of to be expected, even though it's not ideal. But you have to do some empirical choices. The temptation would be to say, okay, I just do a quantum mechanical calculation. I take 2 molecules of water, and then 3, and then 4, and I build my potential. Trouble is, it doesn't work very well, because you are using pairwise interactions, and using as input of pairwise interaction 2 molecules in the gas phase would be just not good enough.
liquid crystals, so it should be simpler than
It
water.
could be. It's not simpler, but liquid crystal have weak first order transitions, and they are never far. We are never very, very far away from the transition. This is a mixed blessing, but it means that some of the details, or very fine details of the potential, are not as critical. Water is a very peculiar thing because of dielectric constant. When we heard of that experiment there, for example, there's another neat experiment where you put an AFM tip there in a Kelvin experiment, and the water comes out by capillarity. Actually, it's not like this. It has a meniscus. It comes out, and you can simulate that. In that case, it's the electric field. But water is very, very peculiar. There's a website on water where it lists the number of unusual properties, and there are, tens of them. So it's a particularly challenging task. But for normal liquid, you can get away with less problems.
Margherita?
Very quickly, very nice. About your droplets, I think just picking up some things that have been said. I think what you do, you fix the total number of particles. So you're doing
Yes.
a canonical simulation, basically. So you fix the number of particles, and that fixes the size of your droplet, because you also fix the temperature and the volume.
Yes, is what
But
I was.
one important question, which is probably referred quickly, I don't know. Did you actually change the size of the droplets by changing? You actually try that, because some of these effects would have a very
You
maybe
mean
a very
pushing molecules in the droplets?
yeah, trying to do a larger system with more particles, with more volume, so that you still be.
The largest that we've
Supersaturated.
done is kind of 100,000 particles. If we did more, I think the droplet would become more spherical.
Yes. So would you expect twist as well? I mean, this chiral thing, if it becomes
Not
really
necessarily.
spherical?
If the
Yeah,
arguments I used is correct, then you could go from one end to the other without. But in some of the old experiments, there were actually pretty spherical droplets which showed the chirality, probably by some other effect.
And even on the surface, when you have the droplet and the two different contact angles, that will probably depend very much on the size of the droplet that you put in.
We don't have a detailed size-dependent study. This is kind of complicated enough. So
Yes.
we have basically one
But it's
droplet
very
size,
important,
and we
yeah.
change the anchoring strength.
Yes. But it's also important to see
It
how
would
this-
be important, yes, but you know, yes, you can change parameters, temperatures, all sorts of things. We try to find kind of an effect that is particularly, you know, interesting to start with, and then.
Mhm, yeah.
But this, I think, is the first observation of the phenomenon of droplet on the surface that has
But
been.
they're still nano
What's
droplets.
that?
How big were they? I think
These are still nano droplets. I'm sorry about that. They are still nano droplets, yes. But you know,
yes.
I mean, nano can be. It's kind of normal. I mean, you can do lots of measurements now on the nanoscale, so they're not.
Yeah.
But you're right. I mean, on the nanoscale, the transition temperature will change. Lots of effect will change. I mean, so.
Well, the contact angle may be difficult to define. It's really microscopic. Anyway,
That applies to many
Yes.
of the things. Even the dielectric constant that we talked about on a nanoscale would be difficult to define.
yes.
You would use a correlation function of dipoles. But yes, I mean, there are many experiments that can be done. Many simulation and possibly many experiments too.
Well, I think we are running out of time, and we thank Claudia again for this talk.